3.2b, we're going to talk about something called residuals. Okay, before I dive into the notes, I want to kind of demonstrate what the residual is. So let's say we have a scatter plot of points, and we want to know what is the best fitting line for this. Well, the calculator computer will find our least squares line. Okay, there's our best fitting line. But you'll notice that this line doesn't go through every single point. It happens to go through these two, but doesn't go through the majority of them. So it's off a little bit. So for these points up here, this line is predicting too low. But the points below the line is predicting higher than they actually were. So this distance between the line and the actual point, these distances are what we call the residuals. Okay? So they can be positive residuals or negative residuals. So they're positive residuals in that the actual value is more than the line predicts. Negative residuals are when the actual value is less than the line is going to predict. So let's look at some definitions. All right, a residual is the difference between an observed value of the response variable and the predicted value by the regression line. It's the actual minus the predicted. So like I was showing you, the actual red dot minus what the line would predict value. Okay, that's what a residual is. So when you interpret a residual, you must reference the size and the direction of the error. Okay, so from yesterday, calculate and interpret the residual for the can that was tapped for 4 seconds and had 260 milliliters of soda remaining. So the actual X is 4, the actual Y was 260. But let's see what the line would predict. So here was the equation that we had yesterday. So if I plug in the 4 for X, I come up with 259.12. That's what the line would predict is the amount remaining in the bottle. But in reality, they had 260 remaining. So to find the difference, I take the actual, which was 260, and I subtract what I calculated, the predicted. So 260 minus this gives me 0.88 milliliters. All right, so I had 0.88 milliliters more in reality than the line predicted. So when I interpret that, here's what it looks like. This can had 0.88 milliliters more soda remaining than we expected. All right, before we jump into the next slide, I want to kind of show you another set of data. This is foot length versus height for a set of 20 people, okay? And you can see the scatter plot and the regression line. Now, how did they come up with this regression line? So it's kind of a complicated deal, and you're going to be given the regression equation, so you don't have to understand how to do it all. But here's what's happening. You learned in algebra that you could take 2 points and you could construct the equation of a line through those 2 points, right? Now, that one line could be constructed from this point and this point, or this point and this point, right? There's all kinds of options of groups of 2 you could have chosen, right? It takes 2 points. It finds the best line, it looks at the residuals from that line, it squares those residuals, and adds up the area in those squares. Okay? So it takes that total, and then it takes another 2 points, a different 2 points, finds the equation of that line, finds the residuals of that line, squares of those residuals, and adds those up. And so it does that for all different pairs of 2 numbers. So we call it the least square regression line because it's looking at all the options possible and it's choosing the one equation. It has the smallest areas and the residuals squared. So it's very complex in the equation, but that's what's happening when we ask for the least square regression line. So as we begin this example about McDonald's beef sandwiches, the first thing it asks us is how do we determine the best regression line for a set of data? Well, it's the line that minimizes the sum of the squared residuals, and that's why we call it the least square regression line. Now, the second thing, is the least square regression line resistant to outliers? Let's look at this example. So here I have a set of data, and the least square regression line has been calculated for me. So the question is, does this line, is it affected by an outlier? Well, right now I don't have any major outliers, but I want you to notice what happens if I throw in an outlier. If I throw in an outlier way down here on the bottom right, notice what happens to my regression line. It tilted down, kind of like a seesaw, right? It pivots down because it needs to capture in this value, and it's going to draw my slope down, but it raised my y-intercept. But what if my outlier was way over here? Did it change much? Not as much. So if my outlier is way out the x-axis, it's going to affect my regression line further than if it's way out the y-axis, just FYI. But do outliers affect it? Absolutely. It works kind of like a seesaw. So is the least square regression line resistant to outliers? No. Think of it like a seesaw. And additionally, if it's far along the x-axis, far out there, it's going to influence that line even more than other outliers. Part C. Calculate the equation of the least square regression line using technology. Make sure to define the variables and sketch the scatter plot with the graph of the least square regression line. So I can make my scatter plot here. Carbs is my explanatory variable. Fat grams is my response variable. I'm going to make my scatter plot. Here it is. I've graphed it. I've labeled my axis. Now I'm going to use my calculator to find the regression line for me because, like we said, it's a very complicated formula, but the calculator does it. So here's the instructions for your calculator, but I'm going to walk you through it. Now I want to show you right here, down here, you need to make sure you turn on your diagnostics. That's going to give you your R calculation and something else called R squared. So let me show you what that looks like. If you find the mode button on your calculator, it pulls up this screen. And if you scroll down, there's two things that say stat diagnostics and stat wizards. You want to make sure both of these are turned on before you do a regression line. It just leaves out some information that you need if you don't have them on, and you'll know it when it doesn't show up on your screen. So once that's turned on, then we can go and start inputting our data. First thing we have to do is input in our list 1 and list 2, explanatory in list 1, response variable in list 2. Then I'm going to go to stat calc, and I'm going to go to number 8, linear regression A plus BX. This is the form we use in stats. Okay. Then the next screen is going to say, okay, where's your X list? Well, it's list 1. Y list is list 2. Everything else is blank. Go down to calculate. When you hit calculate, this is the output you get. It even gives you a friendly reminder. Where does A go and where does B go at the front of the screen? So my A value, my y-intercept, is negative 40.2, and my slope is 1.712. So it says to write the equation. So now I'm going to write it in terms of the context of the question. So my prediction is the hat value. So in this case it's fat. So it's fat hat equals A is negative 40.2 and my slope is 1.713 and my X value represents carbs. So I put my equation in terms of the context of the question. So you got to write it either like this, or if you choose to do y and x, you have to have somewhere that x equals grams of carbs and y equals grams of fat. Okay, sometimes it's just easier to do it like this, but somehow the context has to get included. Part D, we're going to interpret the slope and the y-intercept in context. So here's our equation down here at the bottom. The slope is the 1.713, right? So we're saying for each additional, and what's my explanatory? Carb. So for each additional gram of carbohydrate, we predict the beef sandwiches will have an additional 1.713 grams of fat. Okay, additional takes into fact that it's positive. Notice the context and the units in there. Now y-intercept, remember, is when the x value is 0. So that would mean when there's 0 carbs. What's the fat content? Well, negative 40 grams of fat. So for a beef sandwich with 0 carbs, we predict it will have negative 40.2 grams of fat. Okay, that's just the equation. It's not reasonable. Sometimes these equations don't make sense. So sometimes your y-intercept is not going to be reasonable. That's what this means in terms of the equation. E says to calculate and interpret the residual for a Big Mac with 45 grams of carbs and 20 grams of fat. So these are the actual values. We're going to use the line to find out what's the predicted. So if I have 45 grams of carbs, I'm going to plug that 45 into my equation and find out I get 36.885. That's the predicted amount. Remember, residual is actual minus predicted. So my actual is 29. My predicted, I just calculated, is 36.885. When I subtract, I get negative 7.885. The order does matter. It has to be actual minus predicted. So I get a negative. That tells me that the Big Mac has 7.885 grams of fat less than we would expect. Okay? The line predicts it's at 36 grams of fat, but in reality it's at 29. So it has less than the line would predict it has. Okay, a residual plot is a scatter plot of the residuals against the explanatory variable. They help assess whether the linear model is appropriate. Okay? Is the line the right equation, or should it be some other kind of equation out there besides linear? So what does this mean? Well, if I have a scatter plot that looks like this, and there's my regression line, what a residual plot does is takes this regression line and turns it horizontal right here. So the residual is 0. This is my residual of 0 line, meaning the line was perfectly predicted. Now we know most points don't fall exactly on the line. So what is the distance? It's basically just rotating this line down or to a horizontal position so that you can see where's the residuals. How many of them are positive? How many are negative? And is there a pattern in the way that they fall? So you can see this one is curved and my residual plot is curved. What about another one? What if this? It looks fairly linear, but when I rotate my line so it's horizontal, look, it's pretty scattered. So if I know this is linear, what is my residual plot? It looks scattered. That's what we want. That tells us that the line is appropriate. So you look for an overall pattern left over here. If it's randomly scattered, then the linear equation, the linear model, is the appropriate model for that data. If there's a leftover pattern of any kind, that means the linear model is not appropriate. It may need to be exponential, or it may need to be a quadratic equation, or fill in the blank. But linear is not the right relationship. So lastly, it says construct and interpret a residual plot for the McDonald's data. So this is a great way to use your calculator. Here are the steps. I'm going to walk you through them real quick. So I have my data in list 1 and list 2. The first thing you have to do to get to a residual plot before you go to graphing is you have to calculate the line. Okay, so we've done that in the previous screens. We went to stat, calc, A, linear regression. We generated these values, right? This has to be in the memory of the calculator in order for a residual list to show up. So then if you go to second stat, there's a list of lists. The bottom list will then say residual. If you forgot to do the regression equation first, you won't have this option. But now I need to go to my stat plot, turn it on, and I want a scatter plot. My X list is still my X list, the same list 1. My Y list is going to be the residual list. So I'm going to go to second stat and choose number 8 to get the residual to populate right there. Once I do that, I go to the graph and hit zoom 9 if I need to. And this is what the residual plot looks like. Now, to interpret this, I'm looking to see if there is a pattern in the residuals. So I would say because there's no leftover pattern in the residual plot, the linear model is appropriate for relating carbs and fat grams in the McDonald's beef sandwiches.